Good afternoon. Hope everyone enjoyed their lunch. It's a pleasure for me to be here this afternoon to talk to you about H-period cohort modeling. As I'm going along, please don't hesitate if there are questions that come up and something that I have not made clear, and we can try to resolve things. So, outline for what I will be talking about this afternoon is I want to be talking about the temporal trends from the age, period, and cohort perspective. And we'll be initially talking about what these parameters mean, but then putting them into a statistical model for analysis. And we'll be next be partitioning these effects into their overall linear trend and the departures from that linear trend, or the curvature effects. We'll continue on and talk about using those effects to estimate parameters associated with smoking prevalence, and then to break that down still further into the components of smoking initiation and cessation, to look at the probabilities of making those transitions. We'll then take those effects and we'll combine them and to look at what those contributions from initiation and cessation are to quantify the effects on exposure. And with that, we'll also be looking at how we can modify those effects to account for different aspects of tobacco control, and then finally to look at how we can relate that to population health. So that's basically what we'll be talking about this afternoon. So to start out looking at the temporal effects from the age, period, and cohort perspective, the time metrics that we are looking at here, we have 3 time metrics that are of interest. First of all, of course, there's age. This is the chronological time since birth. And this is, after all, a causal factor for many of the diseases that one is interested in studying, including cancer. Period refers to the date at which an event occurs. And the reason that this might be interesting is that there are often changes that occur that are associated with particular dates and near the time that an event occurs. And if we're interested in cigarette smoking, for example, the introduction of filters and other nicotine delivery systems that change over time, those tend to affect everyone, and that tends to be associated with period parameters. And then finally, looking at birth cohort, this refers to the date of birth of an individual, and this is intended to capture generational effects. And because lifestyle is often sort of set in with particular generations, these kind of might reflect what the lifetime exposure would be to individuals. Now, these 3 temporal effects, they're interrelated to each other. In fact, if we look at a typical display of data, this would relate to age parameters, which are shown here on the vertical axis, and cohort, which is shown on the horizontal axis. Birth cohorts refer to an individual following them in their lifetime. So that if we pick up the experience for a particular individual at this point in time, this would be the particular period and the particular age, and we follow them over time. As we advance time, of course, age is advancing and also period is advancing, and because we would follow the cohort along the diagonal line. Because of this, these 3 temporal factors are related to each other, and so that if we know any one of the 3 factors, we can identify the third, and that's because age minus period plus cohort, that is going to be 0. So in fact, there's a plane that describes all of the parameters that we're looking at. So that's one of the issues that we need to think about when we're trying to describe in a model what these 3 temporal factors are doing. There's also the effect that the way the data are typically tabulated, they're tabulated using intervals for two of the factors. Age and period, for example, are a common choice. So if we use 5-year age groups, suppose we're looking at individuals 20 to 24, and we look at 5-year periods, years 2000 to 2004, the cohorts that are represented in this square of age and period, the earliest cohort that is represented would be individuals who are almost 25 when the interval started in 2000. So these individuals would have been born in 1975. The latest cohort would be those that had just turned 20 in 2004, just when it ended. So these would have been born in 1984. So we have a 10-year cohort group that we're looking at in this particular age period interval, 1975 to 1984. If we slide along, keeping the same age group and look at the next period, 2005 to 2009, the cohort group advances to 1970 to 1989, a 10-year group again, which the center points are 5 years separated from the previous one, but these two cohort ranges overlap, and that's another feature that we have to keep in mind when we're looking at these data. So there are the two issues that they're linearly related to each other, and in fact, one of the factors, the intervals tend to overlap. Now, looking at these two perspectives, we can look at what this has to do with the parameters that we're looking at. Now, this particular graph here is looking at the age-specific lung cancer incidence trends. The blue line is for males, the red for females, and the range of ages here is 20 to 84, and the periods are 1975 to 2006. And you can kind of see what happens here. One of the things that's interesting when you start out here, looking at the trend for females, they tend to go up to decline a little bit, which is a little odd. You wouldn't think that the incidence rates for lung cancer would decrease as women get older. That doesn't make much biological sense, but nevertheless, that's what happens when we look at it from this perspective. And this is probably not the best perspective to be looking at, because we know lung cancer, one of the major factors causing this is cigarette smoking. And cigarette smoking tends to have a pattern that is associated with birth cohorts. And so these have been changing a lot during the 20th century. Especially dramatic were the changes that took place among females. Since the middle of the century, the smoking patterns for women increased enormously. And so that's accounting for a big part of this difference. If instead of looking at it from cohort perspective, we look at it from the period perspective, we look at it from the cohort perspective. This is what we might see. The difference here, the vertical axis is on a log scale. It gives you some idea of what those differences are. Where we started out, the lung cancer incidence rates for men were about 7 times what they were from women. Here they're approaching each other. The other thing that's interesting about these lines is that that pattern of dropping off in the oldest ages is no longer apparent. There's a difference. The shape of the curve is very, very similar, and eventually, of course, they overlap. And that reflects the convergence of the smoking patterns for men and women as time has gone on. So the lines are parallel, and this seems to give a better description, better way of looking at what the temporal trends are for this disease. This, in fact, was an important factor noted in the Surgeon General's report, which appeared in 1964, which was looking and documenting the association between cigarette smoking and lung cancer. And one of the things in this report was a couple of graphs which were showing exactly what I was showing in that animation. And that's these two graphs here, the one on the left being for males, the one on the right for females. The broken line are looking at the age-specific rates for particular years. Now, these data were quite a bit older than the ones I just showed you. The first broken line here are the data from the 1914 cohort and going up for different ages. And the pattern you see is the pattern that I noted before, where they reach a peak and then decline after that. They're doing that for males and also for females. And part of the reason it's more apparent for males is that these are even earlier data. The second perspective they looked at, though, was the perspective of birth cohort, and those are shown on the solid lines here. And those made a lot more biological sense because they kept going up with age, which is what they had expected. Of course, this is going back to very, very early birth cohorts. The first one here is the 1850 birth cohort. And so during that time, those cohorts, the smoking rates for men was changing very rapidly because cigarettes were just being introduced. And so this perspective, in this case, what they were doing is using this as a part of the rationale for confirming the fact that there was a causal relationship between cigarette smoking and lung cancer. Now, so that's kind of the overview of why these factors are of interest. We can also use them, of course, to parameterize temporal trend in a statistical model. If we're representing these as linear trends, we have the three temporal factors, age, period, and cohort, which we present here by A, P, and C. The model for linear trend is shown here. So we have a linear contribution for each one of these factors. And then, but because cohort we can identify just by taking the difference between P and A. So C is equal to P and A. And what that results in basically is a line that depends on just two parameters. And that's the parameter A and the parameter P. Because once we know those two, we can identify the third. The importance of this is that, and the ambiguity that can come into play when these are the parameters that we're interested in, is imagine that there is one investigator that says that, okay, the temporal relationship there is for this particular outcome is shown in the equation on the first line. A second investigator comes along and contradicts this point of view, and he says, no, 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 that's not the relationship. This is the appropriate relationship right here. Now, these two lines, they look very, very different. In fact, in the first line, the slope for A is positive. In the second, it's negative. So it's going up with age, or the second investigator says, no, it's going down with age. Now, what's the difference between these two? These seem, in a way, like a very profound difference. But on the other hand, if we bring in this relationship between these temporal factors and bring in what this is and express it just as a relationship between A and P using that relationship I just described, these are the two lines or two planes that we have, and they end up with this last relationship here. So this is the relationship between A and P, and they're identical. So that indicates that this is not identifiable. So we really can't, within these data itself, say which investigator is right and which is wrong. They're both entirely consistent with each other. And this is the problem where we can't identify it with the data, and that's the identifiability problem that we have in these kinds of models. So the identifiability then of the slopes is not a unique set of all three parameters that exists. These parameters are hopelessly entangled, and the relationship among the parameters means that if one is specified, the other two are identified, but we have to make at least one specification. So for example, if we know that beta P is equal to 0, we have estimated the difference between beta A and beta P, and the sum of beta C and beta P, because if we know from something else outside of the data that beta P is 0, we can then identify what beta A is. Beta A is just the sum of the two, and likewise, I'm sorry, it's beta A minus beta P, because beta P is 0, that's just going to give us the slope beta A, and the sum of the two is just going to give us the slope for beta C. Okay, more generally, so we've talked at this point just in terms of the linear contributions of these temporal factors that we're looking at. Suppose instead of having them be linear, that we allow them to be more general and not force the particular type of relationship that we have. So in this case, suppose we're looking at a model for rates, and we say that the logarithm of the rate is an additive model for these three temporal factors: alpha sub I, pi sub j, gamma sub k. Alpha, pi, and gamma are age, period, and cohort effects respectively. And what we might do in this model is apply the usual constraints. So these are the kind of constraints we might apply if we're doing an ANOVA type of model. Now, another way of looking at these temporal effects is to take them and partition the age effect into linear and curvature components. What this means is that we'll take the effects for alpha I, so this is the ith age effect, and we represent that as a variable I star that represents the age category. It's been centered here for convenience. So we're looking at I minus capital I, which is the number of age groups plus 1/2. So we have that one component, which is linear. The second component, alpha sub ci, that represents the deviation about that linear trend. So we have two components then in this partition of the age group. We have one part that's identified with the slope associated with I star. The second part is the residual about that line, which is the curvature piece, which we're representing as alpha sub ci. Oh, I described how we do that for age. We can, of course, do that, a similar sort of operation for period and cohort. And what we would have then is we would have this same model that I just described, partitioned into these different temporal components. So we have, first of all, for the age component, and we've got the two pieces for that, the slope and the curvature. This is the same thing for period. This is the same thing for cohort. And when we do that, what happens is that these indices for cohort, the cohort index is just the difference between J star and I star. And so we can bring them in just like we did in the first example. It's going to be I star times beta A minus beta C, J star times beta P minus beta C, and that represents the identifiability problem associated with the slopes. The other contributions to the trend, which are the curvature contributions for age, period, and cohort, those are all still there. And so what we have is the curvature pieces for age, period, and cohort. These are all identifiable, okay? So those can be determined from the data. What is not identifiable or not estimable is the individual slopes beta A, beta P, and beta C. While the individual contributions are not estimable, certain functions of them are. For example, Clayton and Schiffler's noted that beta P plus beta C, that is estimable. And that refers to what they called the drift. As you're following individuals in a particular age group, if you follow them over time, what happens is you not only advance period, but you also advance cohort. So the two of them go together. And so to reflect what that change is, the drift is kind of a natural way of describing that. But so that's what we have to limit ourselves to what we're looking at. It's a contribution that's easily interpretable, but it's just a little different from what we're used to in looking at a multivariable model, multivariable regression model. So the relationship then among the slopes is estimable functions of the slopes. We can have an arbitrary x and y, and x times beta A plus y times beta P plus difference between y and x times beta C. That is going to be an estimable function of the parameters. So for example, when x and y are both equal to 1, then what happens in that function, beta A plus beta P, that is estimable. So that's going to be consistent, however, whatever particular model you end up with. If x is 0 and y is 1, then that says that, well, what we have only depends on beta P and beta C. And in fact, it's the sum of the two, and that's the drift. That is estimable as well. So slopes from different models are related to each other. And if you have whatever the true slopes are, slope that you get from your model, or it's going to be related to the true age slope, beta A, plus a constant, nu in this case. So that'll be your estimated slope. Beta P is going to be estimated by the true beta P minus this same constant, nu. And finally, beta C star is beta C plus beta nu. So that sort of reproduces the values that we're looking at. If we knew what nu was, then we'd be all set. But typically what we have to do is we have to figure out what that is from some other factor. And so that's limiting what we're gleaning from the parameters that we're getting from the model to those parameters that are in fact estimable. Now then, so that's kind of the thing we have to keep in mind of the regression model parameters that we are getting from the data that we're looking at. So now let's shift a little bit and look at another part of the problem, is to pose the question in terms of a regression problem. So the outcome that we're looking at, if we're looking at a rate, typically the response is the number of cases that we're looking at. The denominator for our rate is D. So that's would typically be the mid-year population that we're looking at. We're looking at a disease rate, and we would estimate that rate by the ratio of N divided by D. To model this, what's commonly used in the model for disease rates in any event is to look at a log linear model, which is to say that the rate is an exponential of a linear function of parameters. So it's a vector x times a column vector beta parameters. So the model for the expected number of cases is going to be this parameter multiplied by the denominator, which corresponds to adding a log of the denominator into the regression part of the model. The distribution of n, I'm sorry, this computer doesn't have the character set that displays a little squiggly line, which indicates that that's what the distribution is. So the distribution of n is Poisson with a mean of d times lambda. So to give our model, to specify our model, one way of accomplishing that is to say that the outcome is the number of events. The distribution that we're looking at is Poisson, and I'm characterizing the model in this case to a generalized linear model. So we have to give the distribution. It's a log linear model of the covariates. The link function is the logarithm of the rate. And then we have to allow for the denominator. And the way we accomplish that is by specifying an offset term, which is the logarithm of the denominator. So these are three things that we have to give to the software to allow it to go ahead and fit the data. There's also a second approach for doing this in a generalized linear model. And in this case, instead of the number of events being the outcome, we specify the estimated rate as being the outcome. Distribution is still Poisson. That's what gives it the likelihood function that we need to do the optimization. The link is still the logarithm of the rate. And finally, instead of specifying an offset, we specify a weight, and the weight is the denominator. So these are two ways of specifying the model in the generalized linear model framework. The results of the two are identical. The parameters and all the other things that one gets are identical from either one of these approaches. The only difference is it's slightly different, and sometimes you might find it more convenient to use one instead of the other. Okay. Any questions so far?
Clarify what's meant by offset exactly. Could you refer to earlier
An offset, that's sort of a technical thing within the generalized linear model framework. How can I back up here? Okay, see this part of the expression, that's kind of the regression part of the equation. Oops. That's the regression part of the equation. Usually when you have a regression equation, all you have is x beta, right? Those are the covariates and the corresponding regressor variables. But to allow for the denominator, we've added in log of d. So you notice there's no regression parameter associated with it. It's just a factor that's added in. And that's what the offset is. Okay? Okay, so now we have our effects in our model. We want to partition these effects into linear and curvature effects. So what we do from this is we use estimable functions. Drift, for example, is estimable. We apply constraints. That's another way of resolving the problem. One way is to equate two levels of one of the parameters. We might say, for example, that the first and the last period parameters are the same. Or else we can use underlying biology might tell us something about what's going on. So if we have another, we might have another approach for identifying it. But basically the idea here is have to bring in something outside of the data that we're looking at if we're going to identify these parameters associated directly with these temporal effects. One of them is specified, then all of them are identified. Okay, so modeling, let's start by looking at a model for lung cancer mortality. So we have a log linear model with contributions for age, period, and cohort, and they depends on which when we present these variables to a model that we're fitting, when you have this problem with identifiability, unless you formulate it and have made the constraint yourself, the software will crank through and it will make a choice. And it'll give you a set of parameters. So to see what that means, looking at these data, in this case, the choice turns out to be different depending on the order in which these variables are described to the model. So in the first instance, it's described as APC, age, period, cohort, in that order. Okay? The first model, cohort is last. In the second model, age is last. Now, one of the things to notice, the variable that's last, you can see it here with age, is you notice that the last two levels, they set those to be, both of them to be 0. Okay, and that in this particular program that I'm using here, it depends on the one that's entered in last. So in the first instance, it'll be cohort, second age, the third period. And so what the result of that is the parameters that it gives related to all of these are very, very different, aren't they? So they differ by a lot. However, if we look at the intercept, well, I'm sorry, the slope terms, those are in fact very, very different here. So this is just basically fitting a regression line to all these parameters here. That's the intercept and slope that I'm giving here. And those slopes are just very, very different. But the curvatures, and that's what's shown in the second column here, those are basically identical. They're essentially in rounding error here, but they're identical for these factors. So that's what the curvature is doing, and what the graph shows is actually these curvature estimates associated with age. Same thing happens to the other two temporal factors. Period, shown here, slopes very, very different, but the curvatures are identical. And finally, cohort, similarly, different slopes, but the same curvature. Okay. Now, there are other ways of representing trends other than just simply representing them as dummy variables. We might try to smooth out the trends in some way. Polynomials are one convenient way of doing that. And so we can do that. We're faced with the same issue of identifiability, but it provides a curved, it's has a well-structured line that's been specified. And we can have a high degree of polynomial to fit as many points as we want to get the degree of accuracy. The problem with polynomials, however, is that polynomials, if you get very high degree polynomials, what tends to happen is they tend to bounce around a lot. So it's not a very good choice. It'll work pretty well if you have worked up to, say, a second or third order polynomial. That works reasonably well, but it's not great because polynomials don't have enough flexibility to capture all of the types of curvature you're likely to see in practice. What tends to work better are splines. These provide local polynomials, but they're also forced to be linear and to have continuous derivatives. And so they're very, very flexible structure, but they have a smooth relationship that you're looking at for what you're considering. One of these might be linear splines. Linear splines are actually ties in with what we were talking about this morning when looking at join point analysis. A linear spline is basically the same kind of a model that you're looking at with a join point analysis. So we have a series of knots at different points. We have regressive variables, which are the time minus the knot. It's 0 if the difference is negative. It's the difference itself if it is positive. And so what we end up with for the relationship is for that temporal effect is what's shown here. And that's just basically a broken line, which is the kind of model that we were considering in a change point model. An alternative, however, is to take that theme and look at it from the perspective of a higher order polynomial. Cubic splines, for example, are one popular choice. So in this case, in order to apply a cubic spline, we've got the first three terms here, which are the linear, quadratic, and cubic components with respect to the temporal variable. And then we have the third point, which is associated with the knots. So the result is there's always going to be a cubic polynomial relationship. But what this does by not including some of the other terms is that at these knots, the curves are not discontinuous, so they're continuous. And the other thing that you don't do is don't make a sudden change. In practice, we don't think that the curves make a sharp bend. They probably are a smoother bend. And that's what's accomplished by this kind of a model. So in this case, we have k+4 parameters that we're looking at to describe the temporal variable. Now, the strength of cubic splines are they're continuous at the knots, they're smooth at the knots, no sharp bends, and they have continuous second derivatives at the knots. A weakness, on the other hand, is that they can be very unstable at the extremes. So they can show sudden bends or something going on at the ends, the beginning and the end of what the relationship is. What we can do in this case is actually force the lines to be straight at the end. So force them to be linear at the ends, and where it doesn't have that cubic polynomial relationship at the end of the curve. And so for that, we take this one step further and look at restricted cubic splines. These are visually smooth, continuous first and second derivatives. They have fewer constants, and they constrain to be linear in the tails. This kind of a relationship, this describes what those variables might be in the model. So the function there, and then we include that in the model. Now, the limitation here is that the way I've described them, we haven't dealt with the identifiability problem yet. Okay, so this describes a curve that curves and gives us a regression framework for estimating the parameters that'll give us this curve, but we haven't considered identifiability. We need to make these parameters that we're looking at orthogonal to the linear trend, because the linear part is where the identifiability problem comes into play. So the linear parts are not identifiable, but the other components associated with curvature will be. And the way we make them orthogonal is we take all these elements. So that first curve I dropped the first term, which was just a linear term, t naught, and I include all of the others, t1 up to tk minus 1. So those are the temporal parameters that we're looking at. For the linear trend, I have a vector L, which is I minus I, that should be, I'm sorry, I plus 1, not minus 1, divided by 2. And then we find the variables that are orthogonal to that linear trend. And those are the variables T star, which is T minus L, L prime L inverse, L prime T. So those are the regressive variables that we will use, and those will actually be orthogonal to linear trend. And so we've accomplished this factoring into linear and curvature components that I described. So returning to our example on the lung cancer, I'm chosen a set of knots here for age, and the orange line shows the spline curve that we're looking at. It doesn't give quite the same relationship. If we're not happy with that relationship, what we might do is choose more knots, and that'll get closer and closer to what the original relationship was. That shows it for age, and likewise for period. Some of these little blips have been smoothed out, as you can see, with the spline relationship. And finally for cohort. Okay. Any questions so far? All right, so we've now looked at just applying the age-period cohort modeling framework. And what we'd like to do now is to shift into looking at how we can use these models for smoking. And we'll start out with looking at ever smoker prevalence. The data that we'll be using for this, and for example, we have national data on smoking that is obtained from the National Health Interview Surveys. These started in 1965. I'm showing in this slide going to 2012. It actually goes more recently than that. You can now get it up to 2018. So there are a series of surveys that took place here. It doesn't happen every year, but it happens many years. A subset, 16 of these surveys, do provide some information on when the individuals initiated and when they ceased smoking. So that's some additional information that goes back in time and reflects what these individuals did earlier in their lives. Surveys, of course, are cross-sectional. They're longitudinal. Their longitudinal data are not available in these surveys. There's a few surveys that provide some longitudinal data, but they certainly don't have the history of a survey like the health interview surveys. But in this case, the 48 years of history is available in this particular case. Of course, now it should be more than 50 years. 50 years is of course, quite a long time, but of course, no cohorts will have been followed over their entire lifetime. So it still has some limit. We can get a lot of idea about what the patterns were, but not everything. Estimates are not identifiable, of course, without further assumptions. So to look at these data, that's sort of on the time window, and looking at our relationship with age and calendar year, the age ranges in the survey, they start at around 18 and go up to 84 typically, or in some of the surveys, they go even beyond that, beyond 84. That's 84 is typically sort of the upper limit of age. The range for periods are, in this case, 1965. It's going here to 2012, but then now this is an older slide, and now goes a little bit farther than that. But a way of thinking about this is the way that the data that have been identified here, because we're going back in time and asking information on when people started smoking and when they quit, we're getting histories that go back further than that. For example, for individuals who were born in 1890, Some of those will have been picked up in the 1965 survey. Okay, they'll be over 75 years of age, but nevertheless, that gives us some picture of what will have transpired for that group. So we have something going back. We also, if we're trying to project forward, if we want to use the data results from this analysis to say something about what we think might happen in the future, we can also project. We have some of those cohorts now identified very early in their lives, and having that information going forward. Okay, so looking at an example here, we're taking some data from for white females, and the results I'll show you are actually collected for the time interval from 1965 to 2018. So the response here is, have you ever smoked for at least 2 years? The temporal variables are age, period, and cohort, and from that we can get the estimated values from this model. One point I should mention about the estimated variables, as it turned out, I haven't shown you this, but the predicted values are actually estimable functions. So we don't have to worry about the identifiability problem that is taken care of here, because we're looking at something that is estimable. Now, one thing that's interesting about these temporal trends is that you notice that the ever smoker prevalence is always a decreasing trend. And why is that? Well, the reason it's a decreasing trend is because you look at where these individuals are interviewed. The dots are the estimates, point estimates, the crude estimates of the ever smoker prevalence for that survey. The lines are the fitted curves from that. So if you, for example, the red line, this is the 1890 birth cohort, we don't have very many points here, and they're much later in life. Now, in order to be surveyed, for these folks to be surveyed, they have to survive to age 75. And of course, what would happen is individuals who are smokers, a smaller percentage of those will have survived and been interviewed than those that had never smoked because of the differential mortality. So this is one underlying factor that we have to allow for, is the fact that because we're doing cross-sectional surveys, we have to calibrate the data, because going back and picking up this older data, we have to allow for that fact. And that's how we begin that age pattern that takes place. That's how we need to allow for that. Yeah. Oh, I'm sorry.
The differential mortality, wouldn't that only affect ages? Not on the left end.
That's right. It would have a much greater effect the older you get. It would have a very little effect for those. Well, the differential mortality particularly begins to kick in after about age 40.
What we're seeing for the 1890 birth cohort, so the first point that we see is like 1920, something like that. So they're about 30 years old.
That's right.
I see. So it's relatively flat.
Yeah. Well, these curves go back to 1930. Now, what's happening before age 30 is they're starting to smoke. So before that, it'll increase, and that's what we'll capture from the initiation data. So it's just that the peak is going to be about age 30. We're choosing the point age 30 here because that's 30 or 40. That's when, anyhow, it's after that you start getting significant impact for the differential mortality. But the nice thing about age 30 is almost all of the initiation takes place before that. And also before that, there's very little quitting. Okay, that tends to take place a little bit later time, or at least historically, that's what's happened. What's happening these days is very different with e-cigarettes and everything else. So the implications here is that the peak prevalence for the cohorts occurs around age 30. Most smoking initiation has occurred before that. And at age 30, the harmful effects of cigarettes have not had much of an effect. After that, the prevalence declines. Prevalence of ever smoked begins to decline. So this is ever smokers, so there should not be any effect of quitting or anything at this for this particular outcome. So the sample size interviewed is biased with more never smokers still being alive and being able to be interviewed, and that's biased as a sample of what's transpired for the cohort that we're looking at. And we can apply a similar idea to looking at initiation and cessation. And the idea here, what we're ultimately interested in, is to try to describe how this is related to disease history. And so we have a corresponding smoking history that we're trying to describe. So following an individual over their lifetime, there's an initial period before they start, and then there's a subsequent period until they quit. And that intermediate period, we're also interested in the dose, the number of cigarettes they smoke per day. Parallel to this is a disease history, and this is looking at following them over time. They may develop a disease like cancer. They may die from another cause before they've, either before or after the cancer has been diagnosed, or the cancer occurs. We should distinguish between when the cancer starts and when it is diagnosed. There's typically an interval there. And then ultimately, of course, the cancer might kill the individual, so they die from the disease. Now, a simplified way of looking at smoking history is we have individuals who've never smoked, they initiate, they become current smokers, they might quit and become former smokers. And from any one of these strategies, these categories, they can, of course, die, which is something else we have to keep in mind. And this is obviously oversimplified because typically individuals, who have tried to quit, for example, it's not a simple event. You wake up one morning and typically individuals have to try multiple times and they might have relapses and whatnot. Here we've tried to simplify it somewhat. You had to have quit for at least 2 years to be described as having quit at that particular point. If you've just quit for a year, we censor you at that point and say that, okay, we don't really know. We know you tried, but that obviously doesn't necessarily capture all of the difficulties, but we hope to minimize them by making that particular relationship. So we'll start out looking at the initiation, going from never to current smoker. So the probability that we're interested in is the probability that following an individual who is, of course, in a particular cohort, C, the probability they're a smoker at time A, given that they were still classified as a never smoker at A-1. So we're estimating that probability, and if we put that into the model that I've described, what those curves look like is something like this. So these are the estimated initiation probabilities, and these are just the crude estimates. We've done nothing about the calibration due to the bias introduced by the mortality difference. From this, we can look at the conditional probabilities of initiation, and we can accumulate them, and that will give us the estimates of the ever smoker prevalence among those that are alive. So that's just looking at the functional relationship that gives us the probability of ever smoker, and this is not directly derived from the survey. This is derived from our estimated initiation probabilities. What the relationship is between these two is shown here. The red dots are basically like the dots I showed you initially. So these are estimates that are from a particular survey. Now, in this case, the cohort is the 1925 cohort, which is identified down here. Okay. And we see that pattern, that typical pattern of it dropping off with age. In green are shown the cumulative initiation. And you see what happens, the cumulative initiation ends up in the middle of that point cloud. Because that's taking all of the data and it ends up about in the average of what the value is at that particular that particular group that we've surveyed among all these different surveys. So what we see, of course, the middle of the point cloud, it should be going up ultimately to where it is at 30, but it only went up so far. And so this is the problem that we need to do is calibrating the data. And what we do with the calibration is we search and look for a constant that then forces the cumulative initiation to correspond to the point estimate that we got from fitting the model for the ever smokers. So that's the blue line. So that's basically taking these values and calibrating them and forcing them to intersect the red line, which corresponds to the fitted values for the red dots. And see what happens with this with time. Now notice where the cohort index is down here. Okay, so moving this. That's cohort. Okay. Calibration, we do is we NHIS, the survey doesn't give us a direct estimate of mortality, but we can see the consequences of it. What we do then is we empirically look at what's happening over the 45-year history. We calibrate the initial estimates of the initiation probabilities to achieve something that's internally consistent with what we get from NHIS. And the results that we apply is we use the estimates from these adjusted values to describe what happens to the prevalence for age 30 and younger. After that, we use the estimates from that we obtained originally by fitting a curve to the ever smoker prevalence. So to see what happens with that is shown here. So after we've gone along for now, the difference between the green and the blue curve at age 30 becomes very, very similar. So there's very little correction recently, but for the older cohorts, there is a substantial correction that's taken place with these calibrations. And so those give us the estimates of the ever smoker prevalence as we go along in time. See what happens with those data that I just showed you in the smoking initiation probabilities. The broken lines here are the crude estimates that we started out with. The solid lines are those that have been calibrated. So you can see they're actually quite a bit higher than they were initially. And so that gives us smoking initiation probabilities that we can look at and use to describe the whole relationship. Yes.
Think a little bit more about you're searching for a constant that forces the initiation to match with every smoker. How is that constant identified? Like is it as part of this one? Or is there, where does the,
I'm sorry, you're a little hard to understand with the mask. Yeah.
I want to know more about when you said that you're searching for a constant that forces alignment. How is that constant?
Okay. Oh, well, yeah, it's a good question. What it does is it assumes that the initiation probabilities are related to the true values by a constant. So what it does then is it changes that. So you can estimate using cumulative initiation to estimate what the prevalence is at age 30. You have this constant. You change the constant until you get the two to match up. And the algorithm that I use for that is a Regulo-Falsi. It's a common way of solving an equation to find the value of the constant that makes these two the same. So that's just a mathematical algorithm that searches for that constant that achieves what I want it to do.
The cohort, or is that?
It's one for each cohort. Yeah. Yeah, it does that whole analysis by cohort. So similarly for cessation, we have a cessation probability of quitting in a given year, and we get those estimates as well. What's interesting, cessation, it tends to increase over time, and it is rather dramatically. Not absolutely sure why that is. I suspect what it may be related to is people just not feeling well, and it's the cigarettes that are doing that, and so they would take it in response to that, quit in response to that. And so we have a cumulative cessation probabilities, and we can bring the two together, and from that we can estimate other things, like combining these two things together. We can get estimates of not only ever smoker prevalence, which we already have, but then current smoker prevalence by taking that and multiplying it by the cumulative probability of quitting. And likewise, we can take these different values and get former smoker prevalence and finally never smoker prevalence. And we can look at what those patterns are. So here we are for looking at current smoker prevalence for females for different birth cohorts. The approach that we've looked at, we've actually applied this, we've developed it still further. We can use it for smaller data sets. And so we've can use it, for example, for looking at things like educational status, income status, different ethnic groups. And we've also can have a generalized where we're looking at individuals' states. So for example, in this case, this graph is comparing Kentucky with California. So you have a state which has done very little, if anything, to control smoking versus a state that's been much more aggressive at controlling for smoking, California. And so you see the result of that, and this is looking at smoking prevalence, you get a substantial difference. The solid line is for Kentucky, the broken lines are for California. And as I say, we can do this for all of the states, and we've recently done this for all of the states. And part of what's, I think, interesting is that how different the states are. I mean, California here, the trends over time, they've dropped a lot. The difference between males and females was not as great early on as they are currently. They've both had a similar sort of pattern. While some of the other states, like North Dakota here, for females, it's been rather flat, not changed a whole lot. Well, it's dropped a lot for males. Currently, they're not very different, But early on, early in the 20th century, they were quite different. And this, I think, these kinds of phenomena, I think, kind of reflect the social acceptance of cigarette smoking and the difference in that by gender. Finally, I'd like to look at the ways of thinking about what we have in these individual smoking history parameters that we've gotten, to quantify, to use that and bring that around to the health effects that we're looking at, and say a little bit about that. So we have the individual smoking history parameters that we're looking at, and we want to relate that to mortality. Now, to do that, one of the pieces that we need for that, so we've got the smoking histories, but we also need to have by smoking status how that relates to the outcome. So as an example, let's consider how this affects mortality. So for that, if we're going to look at alternative strategies affecting smoking rates, we need to know how smoking status is related to mortality. And so we need then death rates by smoking status. And for this step, there's interesting work by Rosenberg, which appeared in 2012. And this was a way of getting smoking status estimates of mortality. So we have smoking status, the categories being never, current, and former smokers. These are the probabilities we actually just estimated. So what we can do is we can hypothesize a scenario which changes the values. And so, for example, we might want to say that, well, let's see what one of our scenarios might be the actual tobacco control history that took place in the United States. And we might compare that to what we might have expected to take place after the Surgeon General's report in 1964, if there had been no control introduced. Okay? So we can, from that, hypothesize what the changes would have been in initiation, cessation, and so on that did take place as compared to if they had not taken place. This will, of course, affect the prevalence of particular smoking status, E sub S for that scenario. We will have, from the analysis using the Rosenberg method, we will have death rates by smoking status. And from that, we can glean the death rates that we would expect to see from the scenario. So we've got all these pieces that we're bringing together, the smoking history pieces, and also how smoking is related to national mortality to describe what's happening for the population. And to do this, one of the works that we did for this, looking at the effect of tobacco control since the Surgeon General's report. And this is some work we did, was published in 2014. And this was, you recognize, the 50th anniversary of the Surgeon General's report, to try to quantify what in fact had been accomplished in the meantime. So the scenarios that we were interested in is actual tobacco control. So we have what the history actually was. And then we could conjecture what we expect might have happened had the Surgeon General's report that documented the harm that cigarette was causing in 1964, had that not taken place or not been responded to, so that the public made essentially no changes. As part of the history, actually, the public was becoming aware of the harm before 1964. There were articles coming out in various publications, including the Reader's Digest, that was making this information available, and some people were acting on it. Not a huge number, but some were. And you can begin to see that when you look at the data. So the public health measures that were more aggressive occurred after that period of time, and these were basically affecting the initiation and discouraging initiation and encouraging cessation. So the assumption was that there was little change after 1964 as to an assumption, looking at what actually transpired. So it's one way of beginning to look at that. These are looking at ever smoker prevalences at age 30 to begin to get an idea of what the way of formulating this problem would be. The solid lines here are showing the patterns that we actually see from the data. So the dark line here is the trends for males. So one hypothesis was that there was no change after 1964. So we're just keeping it flat after that particular point in time. So that's the actual counterfactual that we considered. But obviously we're uncertain about that. It had been falling a bit before 1964. So one idea would be to, well, let's suppose it continues to fall and it drops from about, what, 78% down to 60%. Okay, so that's one extreme. Another extreme would be that, well, suppose this was just a temporary drip down and it drifted back up to about 80%, which is where it was. You compare that to where we are today on cigarette smoking. It's really quite shocking of where it was back in 1964. But nevertheless, it's interesting to look at. For females, it's even trickier to try to figure out what in fact was taking place. Because in 1964, the trend in smoking in females was actually increasing. And this was in the face of the knowledge that was coming out about the harm that cigarettes were causing. So one idea would be that it kept going and kept going up till about 75%. The actual counterfactual was that it stopped at about 60%. So one idea was that it went up. The second idea is that, well, it may have fallen a bit or a range about those possibilities were the ranges that we considered in this analysis. Remember, we have all of the individual components. So now we can put those together and estimate a particular thing. It's like the prevalence of current smokers. So we can estimate those under the various scenarios. The solid lines here are the actual history. The broken line is the counterfactual, and then we have the range on the counterfactual, the upper and lower limit of the ranges of what we think might have occurred. Beyond that, we can bring in information about we have estimates of the mortality rates by smoking status. So under these different scenarios, we can put this together with the mortality data that we have and estimate how many deaths we would expect in different time periods under these different counterfactuals. And so we have the actual number and comparing that with the counterfactual number, and the difference will indicate how many lives we think were saved by that scenario. So under this analysis between, for the period since 1964, we're estimating about 5,300,000 lives for men. See my line. Yeah, 20, almost 27,000 for women, for a total of about 8,000. So that's 8 million lives that had been saved by the smoking history that we're looking at. Of course, with all the detail that we have, we can look at more refined aspects of what in fact was achieved. Life expectancy, for example, under these various expectancies, because we can estimate the death rates under these different scenarios, we can see how those would have been affected. So for example, for the solid orange line here, this is the life expectancy changes over time for women. Okay, so this is the observed, and this down here, these broken lines are under the counterfactuals. So how much life they had were expected to have going up to 2012 after age 40, they were expected to have somewhere between 42 and 43 years of life, while under the counterfactual, it would have only been about 41. Okay, so there's quite a lot of life that was saved for women, and similarly for men. The difference is actually a bit larger for men. Their smoking rates were higher than women after all. But the other part that's interesting is we can also estimate what these quantities would have been for never smokers. So this is what was achieved. Never smokers, if we had gone down to 0, that would be obviously another alternative that would have been even better, and that's the broken line up here. So what was achieved then is quite a lot, but even more could have been achieved, and that's the difference with the dotted line shown here. So from this analysis, we can make an assessment of what the impact was of the tobacco control that did take place since the Surgeon General's report in 1964. So this, I hope, gives you a bit of an idea of how you can use these parameters to reflect different aspects of tobacco control and different types of policies that might have different effects on these individual parameters, and then use those to assess what the impact would be of those policies. So to summarize then, the Age-period-cohort framework, I think, provides a useful way for understanding temporal patterns in cigarette smoking exposure. Age, after all, has a very strong relationship with both initiation and cessation. Of course, cohort also has a strong relationship with exposure because of the early habits tend to carry forward in time. And modeling in this framework gives us a framework for characterizing the smoking history in terms of the temporal parameters that are important. Modeling of the smoking history, I think, requires consideration of steps. It requires getting some information about the individual components that take place. Initiation, cessation, also the level of smoking is also another important factor that we haven't talked about today, but it's a factor that needs to be considered. Another thing that's important in using data from the surveys are very valuable, but the limitation that they have is that they are cross-sectional. And so when we're going back and using them to retrospectively construct what certain parameters were going back in time, that some calibration is needed when constructing the retrospective information. So the details that we have it can be constructed in terms of assessing, in terms of what the impacts are going to be on particular parameters that we're looking at. So for example, what are the effects of changes in tax law? How will that affect initiation? How will it affect cessation? Clean air laws, smoking cessation efforts, changes in the tobacco market. That's particularly a challenge these days and will be going forward. So the kinds of things that one can begin to think about is, for example, recent change in the legal age that one could purchase cigarettes. What is that going to affect? Well, it'll probably not have much of an effect on cessation, because most of that occurs older, but it probably will have an effect. It will have an effect on initiation, because this is right, age 21, younger than age 21, that's when a lot of initiation is taking place these days. And so the way in which it affects that can be complex, because introducing a law is not going to mean that no one under 21 is going to smoke. It's just going to be a little harder for them to get cigarettes. And so it'll have some effect, but trying to quantify and think about what that effect might be is some of the challenges of doing it. But in separating out the parameters in this way, I think it gives you a framework of beginning to formulate what may in fact transpire because of this. And then finally, this detailed information on smoking provides the detail needed for quantifying the effects of what we're seeing on population health in terms of overall mortality, but there's also other things that, as well. We can look at mortality from particular causes or even morbidity if that's if we have the relevant data to estimate the association of those outcomes with smoking status. And I'd just like to thank the various people I've worked on the projects that I've talked about today. Over time, without them, this would not have been possible. So I'm really grateful for the help that I've gotten from them.